Joanna Hu on the link between morphology and quiescence.
All right. So this is work that I've been doing with Sarah Ellison at the University of Victoria. And this doesn't work. All right, then. No, okay. Okay, so we've been known for quite a while that there are two types of galaxies, the star-forming galaxies and quiescent galaxies. And one of the things that we've noticed is that there's a strong correlation between morphology and quiescence. So quiescent galaxies are normally elliptical with dense centers, and star-forming galaxies are normally diski. So we've measured this correlation in a number of ways. Quiescence correlates with bulge mass, correlates with velocity dispersion, Sirsic N, and core density. Now, you might object that this list isn't strictly morphology, but they are related to each other. So, for example, velocity dispersion is a measure of the random motions of stars in a bulge, as opposed to the ordered motions of a rotating disk. And Sirsic N, if you have high Sirsic N, your early types, and you have a peaked central profile, and that means that you have high core density. Okay, so they're all kind of related to morphology, so I'm going to call them roughly morphology. Now this is the sigma 1, this is the core density within 1 kiloparsec versus stellar mass. And this is one manifestation of this relation that I'm calling the morphology-quiescence relation. Okay, and this is simply that the quiescent galaxies, which are in red, are higher up in this diagram than the star-forming galaxies, which are in blue. Okay, so the quiescent galaxies have denser core masses. So this is a manifestation of what we're calling the morphology-quiescence relation. Okay, so one of the questions we have is, what is the physical reason for this correlation? It's much stronger than the correlation between quiescence and stellar mass, for example. It's much stronger predictor of quiescence than, for example, the environment, halo mass, etc. So we're going to focus on this correlation. So one idea, which is a very popular idea, is that compaction, as Avishai likes to call it, drives gas towards this low metallicity gas, towards the centers of a galaxy. And that infalling gas causes two things. One, it causes a central starburst so that the central core mass, core density, increases. And two, it's thought to also trigger an AGN, which then might be responsible for turning the galaxy red and dead. Okay, so this process, at least the funneling, the loss of angular momentum of the gas, is something that Avishai likes to call compaction. And the loss of angular momentum of gas also happens at low redshift. So this is thought more of a high redshift phenomenon, but it also happens in low redshift in like bar instabilities, for example. And I'm going to call it compaction-like. Just refer to the loss of angular momentum of gas funneling toward the center, causing a starburst. I'm going to refer to that as compaction, or compaction-like. Okay. So others, notably Lilly and Carollo, take a look at this correlation between morphology and quiescence, and they say, well, correlation does not always mean causation. So they proposed a model in which you can get a correlation between morphology and quiescence, in particular density versus quiescence, just by growing a disk inside out, so without any reference to morphological transformation. So their model, what they do is they build a galaxy by adding exponential disks where the scale lengths successively grow with the expansion of the universe. Okay, so that model results very naturally in an older center and younger outskirts. Okay, so this is not a new idea. We've known for a long time that you can get inside-out growth just from the expansion and collapse of dark matter shells. You know, the innermost shells have the lowest angular momentum, and they also are the ones that collapse first. The external ones have higher angular momentum, and they collapse last. So we can get inside-out growth of a disk quite naturally, and we've known this for a while. So what Lilly and Carollo proposed is that if you quench a galaxy early, you're going to be dense. If you quench a galaxy late, you'll be less dense. So you'll be later type according to this model. And so what they showed was that you can get the morphology quiescence relation simply by a lot of early quenching of galaxies. Okay, so we have these two modes of growing a disk. We've got inside out growing a disk, and we also have the mode of compaction, a compaction growing mode. And let's discuss these two growing modes in the sigma 1 versus m star diagram. So by the way, I am using the density within a physical scale instead of a scale radius. And I know I'm preaching to the choir about this a little bit here in Santa Cruz, but the reason why we choose sigma 1 instead of sigma e is because sigma e responds to things that happen in the insides, but it also responds to things that happen in the outsides, okay? Sigma 1, more or less, only responds to things that happen in the inside, so sigma 1 is a good measure of compaction events, or compaction effects. Okay, so let's talk about the first growing mode, which is the secular inside-out disk growth mode. Okay, so because star formation is being added to the outsides, then we expect the total mass to grow faster than sigma 1. Okay, so you expect the evolution of a single galaxy in this diagram to move in such a way that the slope is less than 1. The slope of the actual star-forming relation is 0.9, but Sandy and collaborators have predicted even that the slope of the evolution might even be 0.7. But the point is that m star is growing faster than sigma 1. So the centers should be older than the outsides, and new stars are in the outsides, so the SSFR should be lower in the insides and higher in the outsides, okay? So those are the signatures of inside-out secular growth. Okay, so what about compaction? So compaction events predict a steeper evolutionary path, okay? And so you see this in the Abishai simulations. Barrow et al. Also noticed this. You expect that sigma 1 should grow faster than m star because all the gas funnels towards the center. So compaction adds new stars to the centers. SSFR is higher in the centers. The centers should be younger, relatively speaking. And you also expect the centers to have lower metallicity in the gas. So this is at all redshifts in general, generally speaking. But I would like to highlight that compaction events are also less violent compaction events are also expected at low redshift. So you still also expect a funneling in of low metallicity gas in, for example, bar instabilities. Okay, so we decided to look for these signatures of these two disk growing modes in IFU data. So in particular, we looked in the manga survey. So we downloaded the public data release 14 in the manga, which is mapping nearby galaxies at the Apache Point Observatory. So the public data release is about 2,780 galaxies, but after a whole bunch of cuts in inclination, mass, environment, because we're only looking at isolated galaxies, we're not talking about satellite galaxies. After a bunch of cuts, which I won't get into, we end up with about 500 galaxies. Okay, so this is an example of a galaxy in the manga survey. And here are two example spectra. The red one is from the center region, and the blue one is from the disk. And you can see pretty clearly that the spaxel that's in the disk is quite a bit of a younger spectrum. Okay. So we performed full spectral fitting to the spaxels and in order to create a map like this of age. And this is an example where the galaxy is quite a bit older in the centers than the outsides. Okay, so there are a bunch of details to the full spectral fitting, which I won't get into, but I will say that before we performed the fit, we had to bin the spaxels such that the signal to noise of the bin is at least 20. So you can see that the bins, the patches are the bins, and they get bigger as you go outward. And because we didn't want to keep saying bins of spaxels, we decided to call them baxels for short. Okay, so if you have a better name for it, I'm all ears. But for now, we're calling them baxels. Okay, so in the full spectral fitting of each baxel, we were able to fit emission lines simultaneously, so we can also have measurements of the gas, so SSFR and the gas phase metallicity. Okay, so our goal was to see how these gradients depend on the sigma 1 versus m star diagram. So this is the sigma 1 versus m star diagram. The contours are the Sloan DR7, just kind of all galaxies. The separated in star-forming and quiescent. And then the dots are the manga galaxies, individual manga galaxies, and they're colored by the age gradient. So positive age gradient means they're younger in the centers, and negative age gradient means they're older in the centers. So what you should see here is that when you divide the star-forming sequence into two using this black line, the ones above the line, so the ones with high sigma 1, the ones where we're expecting compaction to kick galaxies up, okay? Those are the ones with positive age gradients. And the ones below are with negative age gradients. So you can actually see this more clearly if you take the average, but I know some people in the audience prefer dots. So I've shown the dots so you can see explicitly what we're talking about. So the age gradient split the star-forming sequence into two tracks that seem to be very consistent with the two growing modes that I described earlier. To see this even more explicitly then, I'm showing the median age profiles as a function of where they are in the sigma 1M star diagram. And you can see that the galaxies above the plot, so this is a relative age, and I can get into that in another point. If you want to ask more about what relative age means, you can ask me. But suffice it to say that the median galaxy has a flat profile at 0. So galaxies that have high sigma 1 have relatively younger stars in their centers, whereas galaxies with low sigma 1 have older stars in the centers. So this is exactly the signatures of secular inside-out growing disk, that's the red line, and compaction events, and that's the blue profile here. Okay, so full disclosure, measuring stellar ages is really hard. It's very error-prone, lots of degeneracies, and so on and so forth. So this seems to be telling us a consistent picture, but we decided to supplement this with the gas information, which is a lot more robust. So here, it's the same diagram, but now colored with the SSFR gradients. And you can see this is a little bit more obvious. The points above the line tend to have negative SSFR gradient. Negative SSFR gradient means that the star formation is enhanced in the center. And below the line, the ones that we're expecting to be doing the inside-out growth, okay, those ones have positive SSFR gradient, meaning that they're lower SSFR in the centers. So I show that explicitly here. So the ones above have this enhancement of SSFR in the centers. The ones below the line have a deficit of SSFR. Okay, and also lastly the gas metallicities. So this is now colored by the gas metallicity, same diagram again, only star-forming galaxies. And so the metallicities the gradients are positive above the line and negative below the line, meaning that the metallicities in the centers of the ones that we're expecting to be compaction-like, there's a deficit of metallicities in the centers. So this is, these are the actual median profiles here. So the ones above the line have a deficit of metallicity in the centers. So here are the three profiles, once again, age profiles, SSFR, and metallicity, and gas metallicity. And these were just for star-forming galaxies, okay? So these are growing in the sigma 1M star diagram. And they seem to be growing in two modes, the inside-out growing mode and the compaction mode. So what happens then when they quench? Okay, so these are the same plots, but just for the quenched galaxies. And there's a lot that you can actually say about the age and metallicity, but I'm just going to talk about the star-forming profiles, just so that we can talk about quenching. So these are quiescent galaxies, and they do have some star-forming baxils, and so that's because they're defined as quiescent if their total SSFR is less than -11 per year, but they something like 30% of these quiescent galaxies still have star-forming baxils. So these profiles are only from the star-forming baxils. Okay, so we're only going to look at the SSFRs. So these are the SSFR profiles. I just put them in this corner. Star-forming galaxies and quiescent galaxies. And what I'd really like to do is to connect these two plots as an evolutionary progression, okay? But in order to do that, I have to make two assumptions to do this. So firstly, if a quiescent galaxy has a star-forming baxil in it, then it's recently quenched, okay? Or it's at the end of its quenching process. So I'm assuming no rejuvenation, okay? So if you want to put up your hand and say rejuvenation, just don't ask me, okay? So for now, I'm just going to assume no rejuvenation. Okay, second assumption is that the position on the quench sequence, so if you have a diffuse core versus a compact core, that's the end point of the evolution that it had when the galaxy was growing in the star-forming sequence. And that's not a terrible assumption because the quiescent population has quite a bit of overlap on top of the star-forming sequence. So when you do that, then you can, with those assumptions, then you can connect the two plots here as an evolutionary progression. So let's look at first the galaxies that are compact. So the compact cores, the ones that we're expecting are on the compaction-like track. So what you can see here is that they're quenching from the inside out. So first they have an enhancement of SSFR in their centers, and then they have a complete drop, a faster drop of SSFR in their centers. So they're quenching from the inside out. And this is reminiscent of the recent result by Sarah Ellison and collaborators, where they showed the SSFR profiles for galaxies depending on where they are in this SSFR M-star main sequence. So the blue curves are the galaxies that are above the main sequence, and the red ones are the galaxies that are below the main sequence. And they also interpret this as an inside-out quenching. So you can connect these to AGN based on the AGN fraction using the Y's cuts, and you find that the AGN fraction actually peaks in the upper part of the diagram where you're expecting galaxies to be kicked up due to compaction-like processes. Okay, so lastly, let's talk about the galaxies that we're expecting to be on the secular inside-out growth track, okay? So the SSFR profiles are roughly the same slope-ish. Maybe they're slightly steeper when they're quenched, but the change in slope is nowhere near as drastic as the change in slope of the compact cores. So what we're arguing here is that the secular growth track seems to quench more uniformly across all radii. So this is an interesting question as to what might be causing this. And so in summary, for star-forming galaxies, the profiles of stellar age, SSFR, and gas metallicity split the sigma-1 M-star diagram into two parallel tracks. So the upper track, where we expect galaxies to be kicked up after compaction, their centers are younger, they're enhanced in SSFR, and deficient in gas metals. The lower track have older centers, their SSFR happens in the outskirts, and they have high metallicity in their centers. And this is consistent with what we're expecting for both secular inside-out disk growth and compaction-like evolution. For quenched galaxies, the profiles of age, SSFR, and metallicity also differ between compact and diffuse cores. And this suggests that both modes contribute to the morphology-quiescence relation. And if we are assuming that this is the case, that both modes are contributing, so we had to make those two assumptions I mentioned earlier, then the result is that the compaction track quenches their cores first, and quenching after secular disk growth is more uniform. Thank you.
Questions? Quick.
You mentioned the fact that you mentioned AGNs for the quenching in the center, but if you have a higher specific star formation rate in the center, the depletion time is shorter, and that's all.
Yes, you could also have that. So that we just
Why
wanted
do you need
to see,
AGNs?
Yes, you can have, well, one question that we need to look at is if at low redshift that's the case, if the depletion time as a function of radius for the galaxies in the upper part of the sigma-1 M-star diagram, if they are indeed short, and we don't know that. It's just in the centers. But if that isn't the case, AGN is one possibility, and I just showed that the AGN fraction correlates with what you'd expect if they are responsible for quenching, which we don't know for sure.
More questions before lunch? Yeah.
Joanna, great talk. I was just wondering, to connect this with the progenitor bias issue,
Yes.
how does then that change the track if the sigma 1 KPC versus M-star relationship is different in the past?
Okay, so that's a good question, and I skipped over that. Basically, if you take a look at the sigma-1 M-star diagram, let's look here. Well, actually, the ones with the arrows. You'd expect the arrows, the evolutionary track to be a little higher up at higher redshift, and then it would go down. And so if you then quench by progenitor bias, the simplest assumption is that they then keep the sigma 1 and M star that they had after they quench and they don't change. And then you'd actually expect the ones that are higher up in the quiescent sequence to be older than the ones in the lower sequence. So you do expect some sort of gradient in age, and that was found actually by Sandro last year. However, what I've shown here, and I had to make the assumption that if you still had star-forming baxels, you were quenching today. So I was looking really and answering some questions about quiescence today.
Okay, I just have one last question. If you go back to this diagram where you split, it looks like the number density, so if you assume that there are two tracks, the numbers are very similar, no? In terms of, and is this coincidence, or is something that, because the compaction events is something that I expect quite stochastic, so maybe it's a merger event, or I don't know, something that, and the fact that it's exactly the same numbers here on redshift 0 is something that it's something that you think about, or is it a coincidence?
I mean, I think about it for the quiescent galaxies, and I didn't have time to talk about that. For the star-forming population, that is a good question. I don't know that the number is significant. Like, I mean, I put a line right in the middle because I just put it in the middle. But it could be even that a lot of the secular inside-out growth track, maybe most of it is inside-out growing, and compaction is only really the upper part of the diagram. But I just kind of arbitrarily put a line in the middle just to show the difference in profiles. In terms of number density for the quiescent galaxies, though, maybe I'll just take this chance to actually show you the last slide, which I skipped. So these are small numbers, okay? So for the quiescent galaxies, this is stellar age, so we can use all the baxels. But when you're looking at the star-forming baxels, and you get a whole reduction, okay? So only 30% of the galaxies have star-forming baxels, and it turns out that most of them are the low sigma 1 regime. So actually, when you think about quenching that happens after the inside-out growth track, that if these are the ones that are quenching today, it seems like most of them are doing the quenching after inside-out growth track, and the quenching after the compaction track seems to be more dominant at higher redshift if all the ones that are missing are actually quenched at higher redshift. And that's consistent with a lot of things we already know.
Okay. So let's thank Joanna and all the speakers of the second test.